million Americans, and of those 5.7 million Americans, 5.5 million of them are over the age of 65. And as you get older, the number of medicines that you have to take daily increases. So we've developed a cost-effective solution that will not only give people suffering from Alzheimer's more independence, but also help their caretakers monitor their daily intake of pills and make sure that they are taking all of their pills on time.
Our solution to this imminent problem is Philli, the smart pill planner. This pill planner uses smart sensing technology to track the daily intake of pills for any user. It notifies the user when it's time to take their pill, and it also notifies them if they've missed a pill, as well as their caretaker or a relative.
So there are a few pill boxes on the market, as you can see. They come in all different shapes and sizes, but the cost can run up to $70, and that includes just a pill box, no additional hardware or software. And so that's why our design is a little different, unique, and cost-effective. So I'm going to go through our system architecture. As you can see, board 1 is our pill box. And you can see there's a wireless network that's communicating between a pill box, user pendants, caretaker pendants, which are worn respectively to the user and caretaker. So an alarm will set off if you didn't take your pill. It will notify the user and the caretaker. We also have a gateway that's relaying the communication using a Zigbee network, and we have the gateway connected to a PC that will initialize initial configurations. So as you can see, an example is an assisted living home. And we have 30 different nodes of our network to represent 30 rooms in an assisted living community. And we have the pendants, the pill boxes, and the other pendants by the caretaker as well. And now we're going to speak a little bit about a riverbed simulation that implements this configuration.
So the architecture that we structured our product on is Zigbee. Zigbee is a wireless protocol similar to Wi-Fi. The range is similar to Bluetooth, however. So this is a simulation that we built on a riverbed. It has one coordinator and multiple intermediary routers, as well as end devices. Those are going to be your Zigbee devices, such as your pendants and whatnot. The scale of this is within 15 meters, so it's a very small system. However, because it is a mesh system, you can continue adding routers and end devices and extending the range. And you can add theoretically add up to hundreds and thousands of end devices. What's really great about this system is it can split the load between different coordinators, different end devices, in more of like a parallel sense, and it also has a self-healing function as opposed to a serial bus, where if it gets cut off at some point, the entire system goes down. If we can actually fail one of these nodes within the operating within the software, and the other coordinators will take up the slack, and then we have this is an example of the things that this is a screenshot of the different configurations that you can do on Zigbee. So you can see it says parameter, the physical layer, and the network layer. The MAC layer was of the greatest concern in the simulation. It deals with data transfer. It also deals with the peer-to-peer check, which is the acknowledgement, and we're going to discuss that in the next slide. So this is an example of a network that's under low stress. You can see it ramps up very quickly, and there's no curve or anything. I should have mentioned earlier. Zigbee is very low bandwidth, so it's like it's I believe it's around the same bandwidth of Bluetooth. So load is always a concern. So the bottom two graphs are a comparison of the traffic sent as well as the traffic received. The traffic received is not. It's a little bit lower than the traffic sent, so you can tell that some data was lost along the way. the other two graphs, that's the MAC data traffic. So it's like it would be the MAC throughput. The second graph is the delay. So you can see the delay waivers. That's basically built up in the pipeline. There's intermittent delays sometimes when the network gets overstressed, and it's something. So simulation definitely help you find out those issues.
So once we completed the simulation, we were able to actually implement this using 2 boards to model nodes in the network. So as you can see on the right-hand side, we have a coordinator and network device, where the coordinator is acting as the gateway and the network device is the pillbox. And this is a beacon-enabled network. So what's happening is the coordinator is sending requests for nodes to join the network. And the method that is used in this is called superframe. And superframe has these things called guaranteed time slots, which guarantees time for data to be received and sent by the nodes. And so that's happening. The network device is sending data and acknowledgements are being sent back and forth. So next, we're able to analyze the packets using Wireshark. And NXP, which is the company that makes the core and the processor that we use, which was the MKW24, has firmware that we can upload directly in order to have this exchange happen. And if you can see in the bolded black box, we have the beacon in the info, and so that signifies the beacon request that we're talking about. So that's coming from the coordinator. And then acknowledgement is sent from the pillbox or the router, and we have a data request and acknowledgement again. After that, we have an association response, which shows the PAN ID. And we configured our PAN ID to be 1234. Both devices have this configured in order for them to join a network. And then the coordinator gives the router a nickname, which is this address you see, 9A93. And each device has a corresponding nickname in order to have data transferred. And finally, we have a link status, basically confirming that our network was successfully achieved and the nodes were joined.
What we're seeing now is the estimated cost of all the components for Philli. For an example, in an ideal case of a retirement home, we would have 1 gateway, 30 wearable devices, and 30 pillboxes with 30 separate patients. The total estimated cost, as can be seen, is $1,142. We have been able to cut costs more than any of our competitors, and our cost includes all our devices and the gateway. Our previous estimated cost was close to $1,500, but this was still a better offer than our competitors, since our cost estimate included all our devices and a gateway, while theirs did not. Now we were able to reduce the cost further due to changes in hardware. Now, as you can see, there are many FCC and IC codes that our wearable device and pillbox have to comply with. I'll focus on one important code for the sake of time. Firstly, one major regulation set by the FCC for devices that generate RF radiation is FCC 15.247, setting guidelines for devices operating within certain bands. In our case of the pendant, which operates in the 2.4 gigahertz band, the FCC commissioned that it must use at least 15 channels, and that the average time occupied within any one channel should not exceed 0.4 seconds within a period of 0.4 seconds multiplied by the number of hopping channels employed.
So I'll be speaking a little bit about the hardware we use for our project. So this is our 3D model that we based our design off of. A couple of key features is, first off, our seven compartment pill planner. And in each compartment, you can see in here, we have a copper plate on the bottom. That's our smart sensing technology that we implemented that will be able to track whether the user has taken their pill or not. That works directly with our indicators outputs. So we hooked it up to each compartment works with a corresponding LED as well as a buzzer within the housing unit. This housing unit, it connects all of the sensors and outputs to our board and PCB, as well as our power components. And we also implemented an LCD screen with user interface buttons, so the user can program the box, so set the time, day, month, year, as well as set alarms for each day. So the way we sense the pills is using capacitive sensing. Originally, we opted for a half mechanical, half optical design, but we found that that design was very costly and the mechanical part was very hard to implement. So we did our research and we found that capacitive sensing will lower the cost of our product significantly, and it is just as effective. So the way capacitive sensing works is we have our copper plate at the bottom, and the copper plate has its own capacitance, and the capacitance of that plate has electric fields that can be found in this yellow area right here. And when a conductor, such as a finger, reaches into the compartment to grab the pill, it adds an additional capacitance. So we use the original capacitance as CP, and when we add another capacitance, we find CF. So when we add those two together, we can find a change in the original capacitance, and that's how we can sense whether the user has taken their pill or not. So these sensors are actually directly wired into our board and can be wired to a send and receive pin. And we use a high value resistor between the two in order to increase sensitivity. So when we increase the resistance, we increase the sensitivity, but a drawback of that is the system becomes slower. So we had to play around with it to find the perfect in-between state, and we found that 10 mega ohms works best for us. So for our first block diagram, this board directly represents our Philli product itself and the PCB within. So we use the MK24D512 microprocessor, and that works directly with our UFL antenna. The UFL antenna is very versatile, it's small, and can be placed within the housing unit, the gateway, and the pendant with ease. And it operates around 2.4 gigahertz. Coming from that, we have, it's powered by a 5-volt USB adapter, 1 amp power, and we have also implemented a backup battery. So this circuit, basically, if the power goes out, or let's say it gets unplugged, it wouldn't lose power or it wouldn't lose memory. It would continue to function properly.
As for our wearable device, which will be a pendant, it will be a small low voltage device. So we're going to use 2 3-volt coin batteries to power it. We'll also integrate a buzzer into the circuit to notify the consumer, and we'll have an RG LED too, where it will show the same status for our pill box via the gateway. Unfortunately, we were not able to develop our pendant as of now due to time constraints, so it will be considered for future work.
So our last board is our gateway. The gateway connects the user pendant to the Philli box itself, and is also connected to the wired to the computer for programming purposes. It's basically the same as all the other boards except with a couple less components. It uses the same processor and RF module and is powered by the USB. And we implemented a RGB LED as indicator lights. So when the LED is green, that means the system is configured and you're ready to go. When it's blue, that means that it's in the configuration mode on the PC. And when it's red, it's not configured yet.
This is the MK24 USB module, which uses the standard 5 volts 1 amp USB. For this, we need 5 wire connections in order for the component to work. The first pin is connected to a 5 volt source coming from the wall outlet. We also have 2 data pins and ID, which is an open connection, and ground. This is essential as it's used for programming the board and will also be used for power switching, as I will show in the next slide. Now, to power our pillbox, we'll be using a 1 amp lithium battery charging board with a mini USB port, Type B. The charging board has an integrated chip, the TP4056, which regulates and limits the rate at which the current is added to or drawn from our backup batteries. As you can see from the diagrammatic representation, we have 2 LEDs integrated in the charging board. The green LED will turn on when charging. The green LED will turn on if our pillbox is fully charged, while the red LED will turn on when charging which will occur only in the case of losing power from the connecting wall outlet or computer, and the pillbox will continue being charged by the backup AA lithium batteries.
So to connect the capacitive sensors with the output indicators, we used a shift register. So basically, each capacitive sensor in the box is connected to the LED and a buzzer inside the box. The shift register basically is what holds it all together, and it has an 8-bit serial in and parallel out. So we were able to create this schematic on Altium with ease and then transfer it to a PCB, which we created ourselves using just a copper plate and etching solution.
So now we're going to move on to the firmware, which there were two main components. One of them, which we spoke about earlier with the network. One tool that was very helpful was Test Tool, which allows you to directly put firmware onto any components that you have. We have the Freedom board, as you can see on the bottom right-hand corner, which we use with Test Tool, and the external debugger, which made putting firmware onto the board seamless. Second, we worked on an LCD display. And so this is the screen that's on the pillbox. And configuring LCD display, it has a lot of components, and one important component is storing memory from the configurations that the user did. Unfortunately, we weren't able to integrate that, and that's something that we want to work on in the future. So looking at the code, you can't really see it on the screen, but a nice way to approach an LCD menu is by having different levels. So your initial screen with your options is the first level. When you select an option, that takes you into a second level. And so that's basically the hierarchy of the code. Second, we use a switch statement to implement the buttons, the up, down, and the selector buttons. So here's the demonstration of the LCD screen, and I'm just going through the options so you can set time, which is for the overall system. You have many options, the weekday, year, hour, and so you can see it changing over here. And then you'll see when you can go back to the main menu and set the alarm. And the alarm only has two options, just the hour and minute. That's all you need to set an alarm, because it's assumed that the alarm will be the same every day of the week.
So I'm going to talk a little bit about the software that we designed for our project. So here's the software architecture overview. We have the user layer, which is the actual pillbox and the LCD screen. The presentation layer, the data layer where data is stored, and we have a web server, which in our case is a website. So the presentation layer manages the interaction between the user and the data layer. So it's in charge of dealing with the data that's sent from the board to the computer or from the computer to the board. So how we decided to handle this was using Protobuf, which is an open source software available from Google. So basically, you write a program in Visual Studio, you prompt the user for certain inputs, you take these inputs and send them to a bin file. So a bin file is a binary file, and it can be sent to the NXP board. The other option was an XML file, but it was easier to integrate the bin file with the board and with Protobuf, so we chose to use that. So here's a simple code for initializing the time on the board. You can also do that via the LCD screen, but we felt it would be a good option for hospital scenarios or an assisted living facility where the primary caretaker might be managing the pillbox. So it allowed them to set the time remotely from the PC. So we can also see the output. So this is a basic reset, setting all the time, minute, hour, all to 0. We can set it to any time. We just chose the reset as this example. So the next part of the presentation layer is handling the data sent from the board to the PC. So the way that we chose to do this was to create a simple graphical user interface in Visual Studio. Basically what it does is it reads the data that's sent from the serial port to the computer, and it outputs it here in the form. So we have the COM ports. It has a drop-down menu. Once you plug in the device, it senses that there's something plugged in, and you can select that port. You can also specify the baud rate. Then you initialize the port, and the port status bar turns green when it's ready. And then you click on the read button, and it will show all of the data that's being received in this box. You can also opt to just send an acknowledgement that it was read and have the data sent to another bin file using Protobuf. So the data layer, we chose to implement the data layer using a database created in MySQL. So the information is sent to a bin file, which can easily be transported back to Visual Studio. So we chose to use MySQL, which you can wrap with C++. So the data is sent to Visual Studio, and then from Visual Studio, it's sent to the database in MySQL. So in the future, we would like to actually integrate the MySQL database with the website so it can be updated automatically. Here is just an example of the relations that we created for our database. We have a missed pill relation, a calendar, and a table for pills. So basically this is where the caretaker could keep track of missed pills, when they're missed, how often they're missed, and it could help in assessing the progression of a person's illness and maybe spot patterns on where they're missing pills more and what time of day. So here we have a demonstration of the website we created for a pillbox. So,
Here we go, yeah.
so basically, it has an about page where it describes the overview of the project. We have our features. We have pictures that describe the pills, how the pillbox senses pills, and also how the LCD screen works. We also have a slideshow that includes different parts of the production process along with a video to watch how it works. Additionally, we have a contact page at the bottom. If the user is having a problem, doesn't know how to configure it, it won't work, you can send an email to the contact person and they can get back to you with customer support issues. We also have the option to sign up. So every pillbox comes with a registration number. You have to register before you can create an account. We've already done that in this example. But the registration number is specific to your pillbox so that nobody else can see your information. It's very simple. You go to registration, and then the registration form pops up, and you fill out your name, your pillbox number, and it sets up an account for you. And then once you're logged in, you can see the metrics on if pills were missed, when they were missed, all of that kind of information.
So this is a demonstration of our final product. Before we play the video, just a quick little description. So first, you can see the wooden box is our housing unit. Also, each LED corresponds to the day that it's over. And we have the user interface buttons on the LCD. Inside of the box, we have our PCB that we made, and along with the board that we used to test it. So for this demonstration, we have set it so the alarm will go off for these 3 days. When the alarm goes off, the LED starts blinking and the buzzer goes off. It's a little low, I don't know if you can hear it, but the only way to turn the buzzer off and to get the LED back to its solid color is for Lisa to take the pill out of the box. And that's basically it.
So we just want to thank the department, especially Dr. Yakos and Dr. Hussein, for enabling us to pursue a project that we were passionate about. And thank you all for coming and listening to our presentation. We'll take any questions, if you have any.
No, I take a question.
Okay.
This is an interesting work that we did. Why we don't approach a company and capital events on a nuclear carrier to try to commercialize on this area?
There is a competition, it was around 50,000 in New York area, so I sent it to those guys. I believe we can consider it in September. It meets the deadline, so we
Yeah.
still have time to finish this and apply for this competition.
Yeah. We would love to pursue it more and do all the things that we couldn't with the time that we had, such as making a wearable device before doing anything with it.
Did you study any reliability study when the device can fail, the limit of the device?
That's part of the simulation.
Fail, yeah.
So the failure of the device, you can actually put that into the simulation. You can do fail this node, and then what it should do is other nodes, other core nodes. If the end device fails, that's a problem. If the end device fails, like for example your pendant, that's a problem. However, that's more of a hardware. That's more of the hardware aspect. It shouldn't be failed. The coordinators, for example, can go offline. Routers can go offline, and in that case, other there's redundancies built into the system. However, because there is one coordinator, if that goes down, the entire system goes down. So.
Excellent project with tremendous efforts. Congratulations.
Thank you.
So we have a question.
Yeah, simple question. First, a comment. I like your logo.
Thank you.
What part of the project? At what point in the project did you make the decision to change the sensor?
It was around the halfway point. We were in talks with people in the mechanical engineering department. We were trying to use springs to deflect enough under the weight of the pill, but we found that when we tried to design our own springs, it wasn't working. So halfway through, we did some research, we looked at other options, and we decided that capacitive sensing was the best way to go.
I read a comment which I was not going to add because for brevity purposes, but this is a nice project that I think would have benefited from an ME contribution,
Yeah.
Membership.
Regarding the sensors, I spoke with the company and he said I gave him the specifications what the diameter would be. What they use different concepts than I'm used to in physics, like how they would have the K values, like spring constants. I gave them all the information that I needed, and I think the final quote was $500 for a set of 10 springs, and we just didn't have that kind of cash.
Yeah. What time, probably. Go ahead. Thank you very much.
Any other questions?
Thank you.
Thank you, guys.